Hello, everyone. We are about to hear Yutaka's talk, applying Elixir for driving small hydropower plants with nerves. So turn it over to you, Yutaka.
Thank you. And hi, everyone. I'm Kikuchi Yutaka from Kochi University of Technology in Japan. Now it is midnight on 5th Saturday in Japan. I'm talking about our trial to apply Elixir for small hydropower plants. This project has not finished yet, but still working. So this is an intermediate report. I hope this presentation be a useful reference for you. Let me introduce myself. I have been working at the university. Also, I am a board member of CloudGrid. It is a startup company of consultation for renewable energy, mainly small hydropower plants. If you want to talk with me, search Kikuyuta in Twitter, GitHub, or the Elixir workspace on Slack. Today, at first, I will give you a background, a small survey of small hydropower plants. In second, I will point out the issues we met while building a plant control system. Thirdly, I will show you our trials to solve these issues. After that, I will conclude this presentation. Before starting the presentation, I want to explain some technical words that you might not familiar with. FA stands for factory automation. When I use the word FA, that means system for industrial use. Scada, SCADA, stands for supervisory control and data acquisition. We often say Scada as the control system in the FA fields. PLC stands for programmable logic controller. That is a kind of computer system simulating electromechanical equipment, for example, buttons, motors, lamps, and mechanical relays. Ichneris is the code name of our project. Ichneris is originally from the name of a virtual power generation plant that appeared in Final Fantasy XV by Square Enix. This slide shows our first experience in building a small hydropower plant since 2016. There is no concrete definition of small hydropower, but in many cases, small means that maximum power is under 1000 kilowatts. The center photo is a full view of the plant. We take water from the river at the intake, shown as at the right-hand side picture. The left image is an inside view of the powerhouse. The equipment transforms the potential energy of the water into electric energy at the powerhouse. The head, or the altitude difference between the intake and the powerhouse, is about 100 meters. A Francis-type turbine gets water 200 liters per second, and an induction generator produces 145 kilowatt at maximum. It has been producing 800,000 kilowatt hour a year. That corresponds about 200 typical houses in Japan. In this experience, we made a Scada of the plant with the legacy or conventional PLC to control the equipment of the plant, and 3 Raspberry Pis to collect log data and for remote operation. We met some issues in this case. One is there were 2 subsystems in a different way. We needed to use different languages to communicate with both the engineers of PLC and the web engineers of Raspberry Pi because their technical standpoints are completely different. The other issue is the reliability of Raspberry Pis that are not for industrial use originally, so 1 out of 3 Raspberry Pis has broken every year. According to this experience, we had tried to make Scada in the other way to unite both subsystems into one. I want to explain the Scada system of small hydropower plants briefly. This diagram shows a typical small hydropower system with power inverters. Water from the river comes to a head tank to remove leaves, silt, and sand. Water gets high pressure through a penstock connecting the head tank and the inlet butterfly valve. Once the inlet valve opens, the turbine is going to rotate and it drives the generator. The inverters regulate generated electric power and the transformer adjusts the voltage for connection to the power grid. Scada must gather all state of the plant and must regulate each equipment. Also, Scada reports the condition to the plant operator and process orders from the operator via internet. I am showing you two more references. This smaller one started in early 2018. It gets water from a sand trap dam that already existed. It produces about 50 kilowatt with a Kaplan type turbine. This image is our smallest hydropower plant we have made before. There is a skiing ground at the upper right of the right-hand side photo. The owner of the skiing ground uses spring water from the ground for making artificial snow at the beginning and the end of ski seasons. He wanted to use the spring water for power generation when he does not need to make artificial snow. This proto turbine produces about 20 kilowatt. In those two plants, we made new Scada. At first, we made a new hardware box that runs Linux instead of using both PLC and Raspberry Pis. We made both a plant control subsystem and remote management subsystem on it in Python language. The box sends log data to AWS and receives operation orders from the operator via internet. We face the other issues while building these hydropower plants. Some problems come from the language selection. We selected Python language at that time with a deep consideration. Basically, Python has no concept of concurrency, so the Scada system runs on just one thread. Sometimes the system responses vary dully, for example, due to slower internet communication or long timing of AD conversion. Talking about small hydropower plants, we do not need hard real-time system because there is no critical control. However, we cannot overlook this kind of dullness. The other problem, Python is a scripting language processed by its interpreter, which may cause runtime crash more than compiler language. We had decided to change the language 2 years ago. Of course, we finally chose Elixir as our Scada language. Everybody here knows how Elixir is lovely. So I am referring briefly to the embedded systems perspective. The advantages of Elixir is mostly coming from Erlang. The concurrency system based on the actor model with Erlang processes is suitable for handling a lot of I/O devices. Also, the crash restart policy makes reliable embedded systems easily and effectively, rather than exception-based systems. Unfortunately, it seems nobody prizes hot the hot reload mechanism of Alan, but it is persuasive to PLC engineers because many PLCs have such function. Elixir's metaprogram scheme or macro is a powerful tool when we encapsulate details of implementation from non-Elixir experts. It is relatively difficult to tell the advantages of nerves. We have felt the comfort of nerves gradually, day by day. Nerves provide some development tools over IP. We use SSH to connect nerves targets instead of a serial line. We also use upload shell to burn firmware on nerves targets instead of inserting an SD card into my PC. These tools improve develop these tools improve development efficiency and remove annoying little actions in development. Nerves Hub is a smart on-the-air platform also working over the IP space. Moreover, Nerves Key, which is based on X.509 public key cryptography model, provides an excellent security scheme for embedded systems. Even we have chosen Elixir and Nerves though, we still have issues to be solved. As I told a few minutes before, there is a deep valley between engineers. The first group is switchboard engineers who also construct PLC systems. The second group is software engineers who construct web and cloud systems. There is a deep valley or a great wall between them, even in their culture. I have wanted to fill the valley or break the wall with a new technology. To remove the great gap, we should solve the issues. The most important issue we think is hardware abstraction. I will explain about that from the next slide. We should consider not only software but also hardware. There are not so many products of Linux boxes for industrial use. Industrial use means the capabilities of maintaining operations under hardware environment. I think the vital key to improving industrial equipment is open or the ecosystem. There are fewer communities for PLC engineers. As for open sources, there is very little stuff for PLC engineers. Web or cloud system engineers tend to avoid to understand hardware details because they have not been familiar with the hardware. So we should encapsulate hardware details, reduce difficulties, and provide simple interfaces as APIs in their jargon. As you know, ARM processes are very fantastic mechanism for programming. Also, in embedded fields, processes are a potent tool for hiding hardware details so we can provide abstract APIs with messages to processes. Elixir Circuit is an essential library of device management, for example, GPIO, I2C, SPI, and so on. Programmers should pay much attention because any process can access I/O device with the Elixir Circuit's functions. A set of careless programs access one I/O device simultaneously that may cause unexpected behavior. To avoid this situation, we made libraries for regulating the sequence of I/O accesses from plural processes. The library prepares just one gen server process for one I/O. Every process that wants to access I/O devices shall use this process. For example, there is only one process named cron LED to on and off the LED connecting to the specific GPIO. Host portability is one of hardware abstraction techniques. Traditional PLCs consist of one main CPU module and other I/O modules without CPUs. We think each module has its CPU because of keeping performance, and maintain the soft real-time property. It should be changeable, that the number of nodes hosts, and also the location in the attached network. Each I/O should be independent of a specific CPU, so I/O devices should have its logical name to be accessed. This picture shows a simple diagram to express host portability. Assuming there are two buttons and one LED, the LED turns on when you push both buttons at the same time. The figure shows that each button has its own process for watching the state press or not. Also, the LED has its own process to turn on or off. There is one more process to click to check the button states and turn on if the condition is established. Note that all the processes should have identical logical names. Of course, you can make those programs working on just one host. Also, you can modify the program split into many hosts, such as 3 Raspberry Pis. It is easy to modify if you made the original program according to the programming principle. This movie shows the case. The left and middle Raspberry Pis charge buttons, and the Raspberry Pi in the right-hand side charges the LEDs. 3 programmers, including me, made programs for the 3 Pis according to the just one specification without any communication each other. It works. So I think hardware abstraction also works very well. I talk about hardware abstraction for web cloud engineers. Now I am talking about an idea for switchboard engineers. They are not familiar with the modern programming technology. This picture shows a sample circuit, a typical self-hold circuit to consider the issue. There are two buttons for start and stop the motor. The motor must keep its state if there is no button actions. In so far as Japan, most switchboard engineers use ladder logic diagram that describes physical elements and their relations. This figure describes the simple circuits. X0 describes the green button, X1 describes the red button, and Y0 is relay that keeps the state using positive feedback. If you translate the ladder into functions in Elixir, you might easily get a naive program. But the program has many inappropriate properties. The program should have just one big loop, and all the elements are in the loop without any modularity. This nature is not suitable for a complex system. Moreover, the CPU runs forever even if there is no state changing. This situation is tough for powerless computing board. The biggest problem is we may not persuade switchboard engineers to use these style technology. We propose a new framework that might be understandable for both group switchboard engineers and web cloud engineers. This is an extended PubSub model. The regular PubSub model transits events from publisher to subscribers. Because the conventional PubSub model only propagates events, we cannot write embedded systems beautifully. So we propose an extended PubSub model that the subscribers should be able to pull the state information from the publishers. This slide explains the description of the sample circuits according to the proposal. I think it is easy to understand for switchboard engineers. We have been developing this framework on Swarm or Sim version 2 pub sublibraries. Let's talk about the hardware we have been developing. Because computing board products for consumers will easily break in harder environments as at hydropower plants. This photo shows the previous version of our PLC boxes named Ichi Armadillo. You can run Linux on them. There is a combo box, a DIO box, and an AIO box from left to right. All boxes have CPU and PoE, or Power on Ethernet. The combo box has some DIO, some AIO, RS485, and so on. The DIO box has 8 digital inputs and 8 digital outputs. All I/O pins are isolated. The AIO box had 8 analog inputs and 8 analog outputs. Now we are developing a new version that uses the same shape and has the same I/O interfaces, named each B. The new feature is that you can use nerve scanner, same as for BeagleBone. We will also test against vibration, physical shock, temperature stress, and humidity stress under the international standard IEC 61131-2. We are preparing cheaper hardware for prototyping because the PLC-like boxes you saw in the previous slide will be relatively expensive. We will use BeagleBone Black or Green as a base board. We have developed a new cape board named each cape for BeagleBone, and they will fit into our original plastic case. We extended the H-cape with BeagleBone Green into a prototyping switchboard, which controls electric power such as 200 volts 3 phases AC power. This is a box. The BeagleBone Green has nerves for I/O control and Phoenix Live View for GUI. These subsystems are combined with Poncho. You can turn on the LEDs via Live View GUI and also turn on the induction motor. Is this the first time to drive an induction motor with nerves in the world? I don't know. Talking about communities, we believe in open communities and open sources. There was no suitable community in my region. We have established a community, Coach EX for Elixir. We have written our knowledge related to nerves and Elixir on a portal website, Kita, in Japanese. I am very sorry for less codes and less documentation in English. One of our missions is disclosing our knowledge into the world. I am concluding my talk. We have developing a new Scada system with nerves for a small hydropower plant according to the ideas I have presented to you. The first plant will start 1 year later with a new system in Nagano Prefecture. I hope I can show you the full Scada system at that time. We think these considerations are useful for small hydropower plants, but also for FA. Therefore, we will try to extend our concept into general FA systems. Before I close my presentation, I want to give my thanks to my colleagues and the communities. Especially thanks to Kazuma and Mitsuhiro from Kochi EX. Also, I want to thank to Emuyasu from Classic EX. Thanks to the communities Nerves JP, Fukuoka EX, Kitaku, Sapporo Beam, and Okazaki Rin Beam. So everyone, this is my presentation for you. Thank you for your attention.
Thank you so much. This is a very impressive use case for Elixir and for nerves and every technology involved. Thank you for sharing your journey across this important project.
Thank you very much.